Hello, I'm AdamRetter. As part of Declarative Amsterdam, I'd like to talk to you about compiling XQuery into the native machine code. So let's take a look at what we've been doing here at Evolved Binary. I'll just share my screen. And I think I need to turn off my video. Okay. So here at Evolved Binary, we've been working on compiling XQuery into native machine code. And this will become relevant later, but recently I've been learning a little bit of the Rust programming language. And we'll see how we get on with that later for this purpose. So what is the problem that we originally started with? And why did we think about compiling XQuery into native machine code? So originally, FusionDB inherited its query engine from XSDB. And unfortunately, that query engine has a few problems. And not least of which perhaps is that it was implemented using a parser generator called Antler, specifically version 2 of Antler. And that is now a very, very old technology, which is not only end of life, but effectively unsupported. So trying to find details of the Antler 2 parser and how you write grammar constraints in it, it is quite difficult. There's not much left online these days. Antler today is at version 4. In the meantime, we have fixed several issues with the engine and made some small incremental improvements. But we feel that there are some fundamental problems for us in FusionDB that we would like to see improved in the query engine. And to do that, we don't think that just continue with the existing query engine is sustainable. We think we need a new start. One of the reasons for that is that there's also a performance mismatch between this query engine that we've inherited as it operates in Java, whereas the core storage of FusionDB is in C++. Now, for those of you that have worked with Java and C++ before, every time you want to send data across that language boundary, there's some overhead involved because of something called the Java native interface that allows these two languages to talk together. So ideally, we want to eliminate that overhead. Also, the current query engine operates over a DOM abstraction. So it's not the XQuery XPath data model, it's actually a full DOM abstraction, which is rather inefficient for the things that we really want to focus on in an XQuery engine. So we've decided that we want a new XQuery engine. But what is it that we really want this XQuery engine to do for us? So one of the things that we're particularly concerned about is error reporting. Unfortunately, the XSDB query engine has a bit of a reputation for misreporting line numbers and column numbers when errors occur, and sometimes giving you the wrong error information. So it might appear to give you an error code or a line or column, but it's not related to the problem that really happened. So we think that excellent error reporting has to be the case. And there are compilers and parsers out there these days that will even suggest fixes to code when they detect that there's problems. And that's something that we might like to take advantage of. The other thing, obviously, that we're very concerned with in a modern system is performance. So we want to be able to exploit modern hardware, taking advantage of things like multi-core CPUs and potentially graphics processing units, where we can offload some of the query operations potentially to graphics cards and things like that. Okay, so what does a XQuery engine typically look like internally? So at a high level, it consists of several parts. So there's always pretty much a parser at the front. So you present your XQuery code as either a file or a string of text, and the parser performs some lexical analysis and then some syntax analysis, eventually generating an AST, an abstract syntax tree. And it's from this abstract syntax tree that you can eventually do interesting things. So one of the first steps you might do is query optimization. And the query optimizer in a database might consult the database to see if there are available indexes. And if there are indexes, perhaps it can use those indexes in your query by changing some of the expressions in your query to utilize index lookups instead of doing direct comparisons. And then once you've done your basic query optimization, you have two different approaches that you might use. One is the approach that XSDB and FusionDB take today, which is to take that abstract syntax tree and interpret it. So each part of the XQuery language is effectively interpreted by a Java program, which then performs some operation for each expression in the XQuery code. And obviously some of those expressions are evaluated against the database. Now, the other approach, which is what we would like to do, is we would like to take that abstract syntax tree and eventually end up with machine executable code that can be run by the processor directly rather than being interpreted. So to do that, you would take your abstract syntax tree. Then from there, you have to produce IR, which is an intermediate representation. So this isn't assembly language or machine code yet. This is a higher level abstraction, but we're getting closer to the machine itself. But this is probably, in most cases, an intermediate representation is still portable between architectures. So from our intermediate representation, we then pass it to a compiler. And it's the compiler that here knows how to produce either machine code or assembly language, which is then compiled into machine code. And then once you have your machine code binary, it has to be linked with any dependencies that it needs. So these might be libraries for accessing the database, data store, or the indexes, or whatever you need there. And eventually you end up with an executable program, basically, which is very, there's really no difference between that and any other executable program on your machine, and you can run it in a very similar way. Although inside a database, of course, the database really takes control of it. Okay, so this is the sort of two sort of well-trodden approaches, if we like. Okay, so what we want to do is create a new XQuery engine for FusionDB. And we've looked at some of the requirements that we have. So based on our anatomy, the first thing that we need to think about is the parser. So with parsers, there are lots of different options out there. Now, they sort of predominantly fall into three categories, which is LR or LL, and then a few other ones that offer different interesting algorithms. I think Stephen Pemberton, for example, has talked about early in his Invisible XML talks as it's a context-free, interesting parser. And I think Tom Hillman may have gone into some detail in some of his XML talks about early as well. LL is more the kind of classic top-down approach. And if you were going to write your own parser by hand, an LL approach is typically the way that you would go. But whichever way you go, these all have different trade-offs, basically. So the algorithms themselves are better at some things than others. And then when it comes to implementing it, you wouldn't typically implement an LR algorithm because it's table-driven. And that requires sort of computation during the parsing. So normally for an LR, you would use a parser generator, something like Yak with Flex or something like that. Now, the advantage of this is that you don't have to write the lexer and parser yourself. You can use Yak or Flex and Yak to generate the code for you. So that's quite nice. You can get going quite quickly because you don't have to really understand how to write a parser yourself. The disadvantage, of course, is that these parser generators have their own grammars. They might not be the grammars that are published in specifications like extended Bacchus NOR form. Instead, they have their own languages, and you have to learn those syntaxes. But still, it's often easier than writing a parser by hand. Another option is parser combinators. This is a fairly new approach and is often used for implementing small domain-specific languages. It's a favorite of mine, actually. I very much enjoy writing parser combinator-based systems. They're very easy to construct, very fast to construct, but everything is written in the host language. So you implement these in C++ or Scala or Java or whatever language your parser combinator library is for. There's some disadvantages with that because you don't have clean, separate grammar that you can refer to. Well, the other approach, of course, is a bespoke approach where you decide to write your own lexer and parser from scratch. As I mentioned, this would typically be an LL, predictive recursive descent parser. It doesn't have to be, but this is probably the easiest, sort of most well-known approach. And the advantage of that is that you have complete control over everything. So you can ensure that you have really good error messages. You can tune the performance to whatever extent you are a great systems programmer or not. The disadvantage is that it can be a huge amount of work depending on the language that you want to implement. We want to implement for XQuery. XQuery has quite a large grammar. It's not one of the largest, but it's by no means a small task. So for our new XQuery parser, as I mentioned, we decided to implement a recursive descent parser, a bespoke one. And we felt that we had to do this because our requirements drove us to a bespoke design. So we really care about the error messages and we're really interested in performance. One of the other advantages that you get from bespoke design is that you can completely control the white space handling. So as well as producing an abstract syntax tree where unnecessary white space is stripped away, we also have the option to produce a concrete syntax tree where the white space is kept. And you can do interesting things with this, like linting and auto-formatting of code and things like that, should we want to. It's not actually on our list at the moment. So with the bespoke approach, you can also decide how much intelligence you want to put into the lexer versus the parser. So lexers usually just convert strings of characters into tokens that represent them. So you might convert, for example, the word function into a token that says this is a function. So what we've done with our lexers, we've tried to make it as intelligent as possible to reduce the amount of work that has to go into the parser. So while we're analyzing the character stream up front, if we detect that we're processing an integer literal, for example, or a decimal literal from the XQuery spec, then we will convert it into a native data type that represents the number rather than keeping it as a string. Also, we have the ability to create subtokens. So we don't just produce a token stream, we produce a token stream from our lexer which has subtokens within tokens as well. So there's almost a little bit of parsing going on there, but it's very minor. But this reduces the load for our parser in the next step. And anybody who wants to reuse our lexer, you get a very intelligent system that you could potentially plug a different parser onto if you wanted to. We do hope to make this open source eventually, and we have decided to implement it in Rust. And we chose Rust because we wanted to do this at a low level. And whilst we could have done it in C++14, which would probably be our sort of language of choice for this work, we felt that Rust was a new, interesting language that has quite a lot of advantages for sort of safety guarantees and creating safe, verifiable code. Of course, if you write it in Rust, it doesn't mean that you can't not use it from C++. You can call Rust from C++ or C if you set up the APIs in the correct way. So we've created a piece of infrastructure software that we hope others will reuse when we publish it as well. Speaking of implementing it in Rust, I would be remiss if I didn't mention that we have struggled with Rust. whilst we have a lot of experience of different languages between our team, Rust was new to all of us. And it is different enough from anything else that we've done that we did have some pain. We considered several times abandoning our Rust approach and rewriting it in C++. The sort of crux of it really is that borrowing in Rust can sometimes require defining lifetimes. And these things are quite unique to Rust and can be quite hard to get to grips with when you start programming Rust. But anyway, we've muddled through and made some good progress, I think. Okay, so this is our new XQuery compiler. So once we've got our Parser and Lexer together that we've written in Rust, we actually have to go from our abstract syntax tree to produce intermediate representation. And then we have to compile it somehow into machine code. Well, we cheated a little bit here, and for good reasons. So we decided, instead of writing our own compiler, that we would use a well-worn, battle-tested system that's out there. So there is a system called LLVM, and it came from the University of Illinois. It's open source under the Apache 2 license. And really, it's kind of a toolkit for building compilers. So it's almost like a compiler toolkit. And what we do is, from our parser, we have our abstract syntax tree. And then we have another application that takes our abstract syntax tree and generates intermediate representation code for LLVM. And then what LLVM does for us is everything else. Once we have our intermediate representation, we don't have to worry about generating native code ourselves or get dirty in sort of architecture specifics. So LLVM is becoming pretty well known now. If you have a Mac computer, it's actually the default compiler for C, Objective-C, C++, and Swift on the Mac. The front end for LLVM, called Clang, CLang, is what provides that. And then the back end churns out the binaries that you need, whether you're on Mac Intel or the upcoming Mac ARM machines. So that's one of the nice advantages of LLVM, is that if you create a front end for it, you can target multiple backends and you don't have to worry too much. Okay. Oh, something else I should mention perhaps is that we're not the first people to attempt to use LLVM for speeding up database queries. So there are 2 or 3 other NoSQL databases out there that have done some work with LLVM for accelerating their database queries. So far, all 3 of the examples that we know of, which are MapDB or OmniSci now, Cloudera Impala for Hadoop, and Postgres are all SQL-focused databases. So we think this might be the first time anybody's tried to do this for XQuery. But we think it could be interesting. For Postgres, for example, they saw a 20% speed up when compiling their SQL queries to native machine code. Obviously, those SQL queries have to be fairly CPU intensive, but it's perhaps interesting. Okay, so this is our anatomy diagram for earlier, and I've highlighted the bit that LLVM does for us, really. It's not entirely fair to say it does it for us. We have to control LLVM and tell it what to do, but it certainly is taking a lot of the work away so that we don't have to worry about it. So really, we generate our IR code here, intermediate representation code, from our abstract syntax tree, and then it goes into LLVM, and out of the other end of LLVM down here comes the executable code. So one of the nice things there is that LLVM has a whole suite of optimizations that it provides, which you can switch on and off depending on your needs. So we don't have to write low-level code optimizations. LLVM will take care of lots of things like code inlining and lifting of variables and functions and things like this. Okay. So let's get our hands a little bit dirty. So if we look at some very simple XQuery here, this is a recursive function that will calculate the nth number in a Fibonacci sequence. And in this instance, I've asked it to tell me what the 33rd Fibonacci number is. And this is great. And at the moment, our XQuery engine will run this, and it's interpreted, and it will give us the result correctly. However, how would we compile this XQuery into native machine code? And what might be the advantage of doing that? So I have to admit, I chose this query because it is machine, sort of CPU intensive. And it's tail recursive. So it's going to call itself over and over and over again. And for systems that don't support tail call elimination, if you increase this 33 to maybe 100 or 200, you'll eventually explode the program stack and the application will crash. But we'll talk about that a little bit more later. So at the moment, we have this code, it's an XQuery, and I benchmarked it on a couple of implementations. So on XSDB, it takes about 6 seconds. On base X, it takes 1 second. And on Saxon 10, it takes about 3 seconds. Now, if I rewrite this in Rust or C and compile it to native machine code and execute it, effectively the same code, it executes in under 20 milliseconds. So 20 milliseconds versus anywhere between 1 second and 6 seconds is quite a huge speed up. So perhaps if we could just take this XQuery, and when the user tries to run it, we transparently compile it into native machine code, perhaps we could get it to execute in something like 20 milliseconds or thereabouts. So how might we do that? Well, the first step is that we have to put the XQuery through our new lexical analyzer. And our lexical analyzer produces a token stream. So this is, the code on this page is the token stream. So this XQuery here, although it's only 10 lines of code, actually produces, and this is with the white space ignored, so this is an abstract analysis, produces 53 tokens. With the white space, obviously there's a lot more tokens involved. And we can run that just to show you that we're really doing this stuff. So this is a little bit of Rust code. I've just declared my query as a string in line for the time being. And I'm going to say that I'm using XML spec 10. I set up some tables for my Lexa. I'm going to ignore white space. I'm going to invoke our new Lexa that we have here, Lexa 2. And I'm going to iterate through the Lexa result, producing the tokens. So let's run that a second. Okay, and as you can see down here, it's dumped out the tokens one after another. So for example, at the top of our query, we have declare, then we have function, and then we have a Q name. So here we have declare function, declare word, because this is a word, and then we have function word, and then we have the Q name, and this goes on and on and on. You can see we have a left parenthesis, which is obviously the start of this. We have a $ character, then we have a non-colonized name. So it's pulling out all the terminal symbols in this XQuery as defined by the XQuery specification. So back to our slides. Okay, so we have our token stream, and that's the output from our Lexa. Now we have our parser, and the input to our parser is the token stream from our Lexa, and it's going to produce, as its output, an abstract syntax tree. Now, that abstract syntax tree is really just a bunch of structures in memory that have relationships, a tree-like relationship between the various structures. So trying to show you those structures in program output is quite hard. So instead, I've drawn a tree diagram here of them. So for our Fibonacci number XQuery, we start with an XQuery module. We know that it's a main module because our parser has detected this. And in the prologue, we come down and we have our function declaration for the local fib function. So that's our recursive function that we're going to have. We have some parameters to our function. Takes a number. It's going to return in a number. And we have a function body, and we have a number of expressions in our function. So if the number is 0, return 0, else. If, and then we have to go on to the next page. Down here, I should mention, this is the main part of the XQuery that basically is the first function call to our local fib function. And then we can carry on. And this is the rest of the implementation for the local fib function. But effectively, when you get to here, we have our addition of the local fib function with the number subtract -1, and the local fib function with the number subtract 2. So these are the tail recursive calls back to our recursive function. And we can see those in our abstract syntax tree that our parser has created for us. Okay. So once we have our abstract syntax tree, how do we actually go from that to generating intermediate representation code, which we can feed into LLVM? And from there, obviously, LLVM can do its business and create our executable machine code. So we have an application, which is basically a glorified visitor pattern that does a recursive descent over our abstract syntax tree. And for each node or structure in our tree, it calls a code gen function. And that code gen is responsible for generating the IR for that node and its dependencies. Okay. Now, actually generating the IR itself is not something that we have to do by hand. We don't need to encode lots of strings of IR into our visitor, luckily. Instead, LLVM provides a builder API, which is very easy to use. And as it turns out, because of this, really, I think, generating the intermediate representation is a much easier task than actually writing the lexer was or writing the parser. Now, we're working from Rust, and there are various Rust bindings for LLVM. We're using Inkwells at the moment, and for the experimental stuff that we're doing, it's working quite well. It's not perfect, but it's quite good. Now, I think I mentioned that LLVM offers lots of optimizations that you can choose to switch on. So once you've built your intermediate representation with LLVM, you can then ask LLVM to do a round of optimizations over the intermediate representation, where it rewrites the IR into a new IR based on the optimization rules that you've set. Now, a couple of the things that are interesting for us anyway, as XQuery developers, is that one of the optimizations is tail call elimination. So if you recall, our Fibonacci function in XQuery is tail recursive. And without tail call elimination, if the stack of recursive calls becomes too much, it will blow up the program's stack. So to avoid that, LLVM can unroll basically our recursive function into a large loop internally, I think is how it works. And it means that we can have as much depth as recursion as we like in XQuery, and the generated IR will always run successfully regardless. One of the other optimizations that looks quite nice for XQuery is there's a lot of dead code argument elimination. So I often see quite long XQueries, many thousands of lines, which have been sort of created a long time ago and updated over time and updated over time. And there's lots of dangling arguments and code in there that really should have been cleaned up and removed, but is effectively unused anymore. So this dead code elimination will just get rid of all of that dynamically for us at runtime. So we don't pay any price for sort of crufty old XQuery that has lots of things in it that aren't used anymore. Okay. So what does our XQuery function actually look like if we were to express it in IR? So as I said, to write the IR, you really use the builder that's provided by the LLVM API. However, the IR that comes at the end effectively looks like this. So this is our definition of our Fibonacci function. And for ease in these slides, for our excess integer type, I've just used 64-bit integer in native terms. And that's going to be the first argument. It's called T1, effectively. The .1 means T1. And then we have our Fibonacci body. And the first thing we do, just like in our XQuery, because this is the XQuery that's been translated into IR, is that we check to see if the argument num is 0. Okay. So we set a register to the value of integer comparison of I64 of register 1 against the literal number 0. And down here, we perform a jump to a label based on the register that we've just set. So this effectively says if T3 is true, so if the number is 0, which we assigned up here, if that's true, jump to this label if body 1, else jump to the label if else body 1. And then we can see we have this label here. So this if body 1 is returning the literal, the constant value, sorry, 0. So this is effectively the XQuery code. If $num equals 0, then 0. So that's all of that there. And then we have the else. So this is basically saying else if $num equals 1, jump to this part of the program, return 1. So if $num equals 1, then 1. Else, we jump in here, which is basically where we perform the 2 recursive function calls. So this is the first call, which takes the value -1. And then this is the second call, which takes the value -2. And we then return the result of making that call. So while this code isn't as succinct as the XQuery, this is an intermediate representation that can be compiled into native machine code that truly represents the original XQuery code that we had. So that's kind of neat, really. We still have a bit more to kind of do before we can execute this. We have to set up native code that effectively calls this function. But for succinctness in this slide, I just wanted to show the function body because that's the interesting part. And it does actually show how to call a function. So it would just be more of this really to call this function. Okay. So where are we at today? We're still quite early stage with this native compilation, but we think we are starting to prove that it's interesting. So our Lexer is working, our Parser is working. Now, of course, if we decide we don't want to do native compilation, the Lexer and the Parser are still completely valid. They're just generating token streams and abstract syntax tree. From there, we have some very experimental intermediate representation generation and just-in-time compilation. So we generate the IR with the LLVM builder, and then we ask LLVM to compile it and execute it. So we still have quite a lot of work to do before we have a new XQuery engine. Of course, we have to go and re-implement the XQuery standard library, the functions and operators. But it's been very interesting. And thinking about the future, LLVM has some interesting properties. So for example, one of its targets is WebAssembly. So anything that you can compile with LLVM, like C, C++, Rust, or maybe even XQuery, you could target WebAssembly. Which maybe that means that we could then run or call XQuery from web browsers and Node.js. Also, one of the targets for LLVM is the GPU, so the graphics processing unit, which is still somewhat untapped for databases. The only database that I'm aware of that uses it is OmniSci-MapD. And there's a very interesting article online called The Billion Taxi Rides with MapD, which is worth reading about if you want to see how they used LLVM to optimize their SQL processor to process billions of taxi rides. Okay. Well, thank you very much. That concludes my talk. And if you have any questions, please feel free to ask them. Thanks.